Hey there, welcome back to Short Takes 331. In this video, I want to start a new series called Toward Quantum Monte Carlo. And in this first episode of this series, I want to talk about the Trotter-Suzuki factorization, which is an essential component of all quantum Monte Carlo simulations, or at least the majority of them. The fundamental object in equilibrium thermodynamics, which is the goal of this series, is the partition function. In our case, it will be the grand canonical partition function. And by the way, when I say that we're starting this series on quantum Monte Carlo, I'm going to focus on finite temperature quantum Monte Carlo, but a lot of what we're seeing is going to be applicable to zero temperature or ground state calculations as well. So in this equilibrium thermodynamics context, then we have this grand canonical partition function, which in quantum mechanical terms corresponds to the trace of this complicated operator. And this operator then is the exponential of minus this parameter beta, which will represent the temperature, it's the inverse temperature, multiplied by the Hamiltonian minus the chemical potential times the particle number operator. So once again, this is the trace of e to the minus beta h minus mu n, where beta is the inverse temperature, mu is our chemical potential, h is our Hamiltonian. Typically, the Hamiltonian will have a free part, which will be the kinetic energy, and there will be an interaction part as well, usually a two-body interaction or higher body interaction in the cases where you're interested in high density, such as in nuclear physics or in other contexts. And n is the particle number operator. Typically, this doesn't have to be a particle number operator. It could be some other conserved quantity. It could be an angular momentum. It could be a total momentum operator. It could also be some other conserved charge. No matter what it is, it will be a commuting operator with the Hamiltonian. So that means that it's a conserved quantity. And that means that you can simplify this exponential that appears here, that is the core of our interest, quite a bit. And so this is a crucial separation that occurs when you have a commuting quantity, a commuting operator, in this case n. So the fact that h commutes with n means that you can separate this complicated exponential into a part that depends purely on the Hamiltonian and a part that depends purely on the particle number operator. And if you implement that factorization, then you can, in a way, forget about what happens with n for the technical side of the calculation. Of course, you do need to include this part in your final calculation, but for the intermediate steps, you can set it aside and not worry about it too much. Now, if you actually want to pursue a route that takes this factorization more seriously, you end up with an expression of this sort, where you break down this trace of e to the minus beta h minus mu n into a sum over all possible particle numbers from 0 to infinity of the fugacity to the nth power. The fugacity is just e to the beta mu, so it's this factor that appears here. So we're doing nothing else other than separating this trace across subspaces of fixed particle number, and so you sum over all those subspaces of fixed particle number, you get z to the n and q sub n, and this q sub n is what we usually call the canonical partition function, and it's a trace over the n particle subspace of e to the minus beta times the Hamiltonian. And so this breakdown done here, if you take it seriously and you proceed order by order in powers of z, then you're doing what's called the virial expansion, which is something that I've done quite a bit in my research with my students over the last few years. If you don't do that, if you come back to this, but you do account for this separation, then you can proceed towards what we are interested in this video, which is the Trotter-Suzuki factorization. In other words, the main difficulty in dealing with z is that this operator is essentially impossible to compute as it is. We've separated the particle number, but now we have to deal with this object which contains all the dynamics of the system. Why is it so hard to deal with? Because of the interaction, and because the interaction doesn't commute with the kinetic energy. If these two operators commuted, if t and v could be exchanged in their order, then it would be very easy for us to say, well, e to the minus beta h can be factorized into a kinetic part and an interaction part, and we would be essentially in the same position as in classical dynamics. And so, which is what happens. So when these two things actually commute, you're basically doing classical physics. But in general, that's not true. In general, you have this equation, so e to the minus beta h is not equal to e to the minus beta t times e to the minus beta v. And so we have to do something else to really account for the quantum mechanical nature of the problem. The Trotter-Suzuki factorization is then a generic name for a family of approximations where we try to account for this difference between these two sides of this inequality, of this equation that is really not an equation, the fact that this is not equal to this. And here's then the first idea. Step number one is that the first thing you do is you say, well, e2 minus beta h can be written as multiple factors, and here we're going to use n tau factors of the form e2 minus tau h. And this decomposition is exact. We're assuming here that we wrote beta as some factor times some large integer, so n tau is some number much greater than 1. You could start with 10, you could imagine it's 100, maybe you could imagine it's 1,000. No matter what it is, this parameter gives you a sense in which tau is small. And so then e2 minus tau h is then something you can approximate because you have a parameter here that is small in some sense. How? In what sense? Well, that depends, of course, on what is in h, and that will be regulated by how high we make this n tau, which will be much greater than 1. But putting that discussion aside, then we're in a position to go to the second step and tackle e2 minus tau h. So now the simplest approximation you can implement for e2 minus tau h is to say what we said above was incorrect. So this, of course, is not true for finite beta, but if tau is very small, then we may be in a position where we can approximate with some hope e2 minus tau h by e2 minus tau kinetic energy, e2 minus tau interaction. And we'll see that this is actually correct up to a point. So there's an error that starts at order tau squared when you consider both sides of this equation, or quasi-equation that I wrote here with an arrow. So we're trying to approximate this with this. That's why I didn't write an equality here. We could also implement a different kind of approximation scheme. This, by the way, this is what we call the simplest Trotter-Suzuki factorization. And here's our next Trotter-Suzuki factorization, where we separate kinetic energy by using a more symmetric decomposition, where we have a kinetic energy divided by 2 on the left and a kinetic energy divided by 2 on the right. And in this one, the error starts at order tau cubed. And this is interesting because the Hamiltonian is symmetric. It's a symmetric operator. And so, in fact, it is a Hermitian operator. But this one is not. Whereas this one, once again, is Hermitian. So you reveal here with this approximation some, or you encode in this approximation some of the properties of the Hamiltonian that you would expect. So this is a symmetric object, as symmetric as this one, whereas this one is not. So this one you would expect it to be better, and in fact it is. For this one, the error starts at order tau cubed. And you can go on and generate more and more complicated approximations. But first, let me show you that how it comes about that this is correct up to order tau squared, and this one has errors that start at order tau cubed. So this e2 minus tau h is something you can expand in the Taylor expansion. And so these are the first 3 terms of that expansion: 1 minus tau h plus tau squared over 2 h squared. Whereas for this first, the most basic approximation, we have, if you expand both factors, you get 1 minus tau t plus v, which of course is the same as h. So far so good. But then when we go to the next order tau squared, we find that all the t's are always going to be to the left of the v's. And so this is not equal to h squared over 2. So h squared over 2 will have tv and vt. But there's no hope to have t to the right of v in this expression. All the t's will appear to the left of v. And so that's why we're making already a mistake at order tau squared because of this operator that is incorrect. These two are correct, but this one is not. Now, for the last one that we saw, the second one that we saw, we have this symmetric product, which is nice, looks interesting. And so when we do the product here, if you expand each factor into a Taylor series up to second order, then you'll find that it's the product of all that starts with a 1. That's of course correct. We get at first order t plus v, once again correct, same as with the previous decomposition. And then when you go to order tau squared, you also get something that is correct because you have t squared over 2, v over 2, and then you have this symmetric product divided by 2, which is what you would expect of h squared. This should be h squared here divided by 2. So then this is correct, and then we're in business up to order tau squared. But when you go to order tau cubed, I didn't write it here, but you would start making a mistake. If you go to order tau cubed, then you'll see that we will have a problem. And so the story continues. Of course, you can come up with higher order approximations that are better and better, but they will be more complicated. So the conclusion then is the different flavors of this decomposition will give you different levels of correctness, but it will also give you different levels of complexity, and usually they will compete against each other, against one another. So this factorization is essential for all sorts of applications in many-body physics, even in some classical cases. But notably in quantum computing applications, people use this Trotter-Suzuki factorization, or some flavor of it, quite a bit. And so this remains an area of research and is not only essential for quantum Monte Carlo at finite temperature, which is something I've done for a long time, but also for quantum computing, if that's an area that interests you. I hope you find this video useful. It's just a nugget of information building towards what we call quantum Monte Carlo. We'll talk about that quite a bit more in upcoming episodes of this short series. So if you like this video, if you enjoyed it, find it useful, please consider liking and subscribing to the channel, and I will see you next time.